How are you doing? Good. All right, ready for the weekend? Remember, we have a test on Monday. The test is over sections 2.1 through 2.5. We're currently in section 2.6, covering the material there, but that section will be on the next test. Also, originally, I had the assignment on 2.6 due on Sunday. I've moved that to Thursday. Okay. We should finish up the section today with studying for the exam on Monday, and then when I have the opportunity to ask questions afterward, I moved it to Thursday. Okay, so on your syllabus, on the list of due dates, it says it's due on Sunday, but I moved that to web assign. You should see that reflected in web assign. What questions do you have? Everything's going all right? You're all ready for the test? You can take it today? Yeah? All right. Anyway, so let's continue on then with our discussion in the transformation stuff that we talked about last time. So we did, I think, one example or two examples? Good. All right, so let's see if we can just do some more examples here. Basically, we're collecting information about what we need to do with certain graphs to figure out how to get a new graph from an old one. So let's look at this example where we've got g of x is 2 times square root of negative x plus 2 minus a 3. So much like what we talked about last time, let's collect what information we have in there about what types of transformations we might have and how many we might see. So notice we've got this number on the outside multiplied. All right, well, before I do that, what should you think we should use for the base graph? Let's start there. What should we use for base graph? Yeah, the square root function, right? Square root of x. Okay, so our base graph will be y equals square root of x. Let's start there. Sorry, we should start there first. Then we'll go through the transformations. What does your graph of y equals x squared look like? Yeah, it goes that way, right? Starts with the origin, goes up into the right. It's half of a sideways parabola. Okay. So goes through points like 0, 0, 1, 1, 4, 2. Like so. There's where the graph, that's our base graph, right? Our y equals square root of x. So the idea here is to transform this graph into the one that we're looking for. All right, so let me scroll back up to, or at least zoom out a little bit, to the problem here. If I can, there we go. Like we mentioned last time, we want to start identifying what transformations we have. I think we see 4 separate things going on here, like we did in the last example that we did on Wednesday. I've got this 2 on the outside. I've got a negative sign here on the x. That's different than what we've seen before. I've got a plus 2, and I've got a minus 3. I told you last time that I think it's easier to read from left to right and go with your transformations that way. In order to make that work every single time, if you've got a coefficient on the x, you need to factor it off first so that you can see what's going on. So if I factor out the negative, I would be left with x minus 2 and then minus a 3, like so. Just factor the negative off the x, it'll flip the sign on it too. So that's our g of x function. All right, so remind me again, what's this 2 on the outside going to do? So it's multiplied, so is it going to shift or is it going to stretch? It's going to stretch, right? Which way is it going to stretch? Yeah, it's going to be vertically, right? It's going to be a vertical stretch. Why is it vertical? How do we know it's a vertical stretch rather than a horizontal one? The 2 is on the outside, right? If it's on the outside, it affects the outputs, right? So your first transformation will be stretch vertically by a factor of 2. Let's go ahead and just handle that now. If we stretch vertically by a factor of 2, what happens to the point here at the origin? Stay the same, right? The output is 0, multiplied to 0 by 2, you get 0. Where does this one go to? Yeah, it goes up to an output of 2, right? You multiply the output by 2. So instead of being at 1, it'll be at 2, right? Where does this output end up at? 4. Okay. You'll notice when you go through the WebAssign problems, one of the things it wants you to do is track where points move to under these transformations. So the point here, that was weird. The point here at 1, 1 gets moved to 1, 2 because it gets both that output got multiplied by 2. This at 1 was at 4, 2. Now it's at 4, 4. And so that would be what, and this would be what your graph would look like after that transformation. Again, going from left to right. Why does that to me? Again, going from left to right, the next thing we come across is that negative sign, right? Now, in the previous problems we've done, the negative sign is on the outside, so it affected the outputs. When it did that, it flipped it upside down, right? Top, bottom. This negative sign now is on the inside, so it's going to affect the input. So instead of flipping top, bottom, it's going to flip left, right. It's going to go this way. It's going to flip, it's going to reflect across the y-axis. So again, let's track points. Where does 0, 0 go when you flip it across the x-axis, or the y-axis, sorry? It doesn't go anywhere, right? Where does this point here at 1, 2 go to? So we're going to flip left, right. It's going to go to negative 1, 2, right? It's going to take the input and make it negative, right? Where does the point at 4, 4 go to? Negative 4, 4 over here. So you'll get a graph that goes that way. Again, one of the reasons why I'm focusing on the tracking points thing is because, again, your WebAssign problems will ask you where the points end up. It'll say this point started here. Where does it go to? And it'll put in the order pairs for where it ends up. Okay. That's why I've been tracking them. All right. So for the third one now, what's the next thing we notice in our function? The negative 2 on the inside, right? Again, it's on the inside, so it affects inputs. What does that tell you when you have a minus 2 here now? Yeah, it's going to go right too. Good. I don't know why it flickers sometimes. This is, and the reason why I factored out the coefficient is so I could do that read from left to right thing. If you didn't factor out the coefficient first, you would do your shift and then your flip. It goes kind of backwards for what we've been talking about. So that's why I like to factor it out first and then just do it in order. Remember the minus sign on the inside, you treat it opposite of what you think you would, right? Negative x values go to the left, but when we're subtracting it, we're actually moving it to the right when it's affected on the inputs. Okay. So if we go right 2 units, the point at 0, 0 ends up at 0, 2, right? The point at negative 1, 2 ends up at 1, bless you, 1, 2. And the one at negative 4, 4 ends up at Negative 2, 4. So we've got that graph. And we've got one more to go. Why do you have such problems letting me change the color? All right. Finally, the last thing we do. My goodness. What's the last thing we notice on this function? The minus 3 here. Minus 3 tells you, what is it going to affect the x's or the y's? The y's, and it's going to go down 3. Good. So our final graph will be taking everything and moving it down 3. We're working off that last black graph that I drew. So this point at 2, 0 ends up at where? 2, negative 3. Good. This point at 1, 2 ends up at 1, negative 1, right? And we're subtracting the 3. And then the other one goes down 3, so it ends up at negative 2, negative 2, 1. And we get, this is our final graph. So again, on WebAssign, it might ask you the point 4. You started with the point 4, 2. Where does it end up at? Where did that 4, 2 point finally end up at? Where did that correspond to? Yeah, this one here, right? It ends up at negative 2, 1 by the time we finished up. So again, that's what the WebAssign is going to ask on some of those problems. Start with an ordered pair. Where does it end up? Well, if I start here, multiply by 2, flip it, move it over 2, and down 3 would end up there. So you can just track the point that way. What I'm going to be looking for when you're doing something on an exam, I'm going to ask, it's going to be this type of thing. I'm going to ask you to list the base graph. Tell me what the base graph is. Tell me what the transformations are, and then sketch a graph based on the transformations. If you tell me what the transformations are, and you mess up the graph a little bit, you're still going to get most of the points because you figured out what the transformations are if they're right. Okay, so make sure that you understand how to get these written down because that's what I'm going to be looking for on quiz exam type of thing. Okay. Any questions on this one? Yes, go ahead. Why did what sign change? And we go down, it's negative x minus 2. I factored the negative sign out, so if you redistributed, you'd have to take that negative to both of them. So when I pull a minus sign out, it's going to flip that sign from a minus to a plus. And the reason why I'm doing that is so we can do that concept of being able to read straight from left to right to get our transformations. Okay. If I don't factor the coefficient out first, you have to do the transformations inside in the reverse order than you do the ones on the outside, and I just figured that for you. So you just remember to factor out the coefficient first, so you can just read from left to right. That's why I do it that way. Other questions at all? All right, let's do another one here. Again, the idea, first thing I want you to do on these problems is identify what the base graph is. What do you think we're going to use for a base graph in this one? Cube root of x, right? Because that's the function that we see in there. Okay. So we'll start with our base graph. Now I'm in red, of course. All right. What does cube root of x look like? What does your square root just look like? Square root went like that, right? Cube root looks almost the same. It just also continues on the other side. Remember, your odd roots, you have the negative piece on there. The even roots only have the right-hand side. So your base graph, some points on there will be 0, 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 2, because cube root of 8 is 2. And then you'll have the negatives 2, 3, 4, 5, 6, 7, 8 over here. And again, I'm not looking for perfection in your graphs. I just want you to make sure that you understand the idea of what's going on. So there's a basic shape for your cube root of x graph. So let's go back up here to the function. Got several things going on in this one. I've got this negative out in front. I've got a 4. I've got a 3. I've got a 9. And I got a -2. So I got 1, 2, 3, 4, 5 things going on. Lots of things going on in this case, but there's 5 different transformations. But just like I mentioned in the previous example, the first thing I would do is factor off the coefficient on the x so that we can read from left to right. If we factor the 3 off the x on the inside, what are you left with? X plus 3? Yeah. That'd be the first thing I would do. Factor off the coefficient on the x, and then again, we can read the transformations off from left to right. Okay. First thing I hit is that negative sign, right? What does the negative sign tell you to do? Flip it which way? Yeah, over the x-axis, right? It's going to be a top-bottom flip this way because it's affecting the outputs again. So transformation 1 is reflect across the x-axis. I'm going to write down the transformations and then we'll do the final graph at the end here. Because I want to practice again with figuring out where the points go to. We'll reflect across the x-axis. The next thing we cross is that 4, right? What does that 4 do? Yeah, it's a vertical one because it's on the outside. Is it a stretch or a shift? It's a stretch, right? Because it's multiplied, correct? Anything that's multiplied is going to be a stretch or a compress, okay? So this is going to stretch vertically by a factor of 4. And again, what that means is that we're going to take all of the y coordinates and multiply them by 4. Take all the outputs and multiply them by 4. That's what that means. Okay. We okay with those two to start with? So we've got vertical reflection, vertical stretch. This is what we're going to multiply all of the x's by, or excuse me, all the y's by. Now let's move to the next one on the inside here. This is now to the x's, right? This is on the inside. It's going to affect the inputs. It's going to affect the x's. We already talked about that when what you do if you add or subtract, it's kind of backward for the x's, right? When we add, we shift to the negative direction for the x's. When we subtract, we shift to the positive direction for the x's. It's backward. The same thing is true here. When you multiply by the 3 on the inside, it's going to have the exact opposite effect. So instead of multiplying all the x's by 3, you're going to divide them all. Okay? So this is actually, we're going to compress horizontally. By a factor of 1/3. It does the opposite. I would personally like to think of the number multiplied on the inside as a speed factor. The graph gets drawn out 3 times as fast. Okay. So if I think about it getting drawn out 3 times as fast, I have 1/3 of the space to get drawn in. That's why it's compressing it this way. So again, just try to remember that whatever is on the inside is the opposite of what you think it should do. So instead of multiplying all the x's by 3, we're going to divide them all by 3. What's the plus 3 tell you to do? Shift left, good. 3 units, and then the minus 2 tells you shift down by 2, good. All right. Are there any questions about how we listed the transformations before we start tracking these points and where they end up? It's okay? Bless you. All right. So let's track the points before we try to re-sketch anything. Let's just track the points and then do a final sketch. Okay. Let's track 0, 0 to start with. The first transformation is reflected. What happens to the 0, 0 when you've reflected? Nothing. Good. Stretch vertically by a factor of 4. What happens to it? Nothing. It's still on the x-axis, right? So the first two transformations don't do anything to 0, 0. Compress horizontally by a factor of 1/3. What happens? Nothing. So it hasn't moved. The only thing that happens here now to move it is the shifting, right? We're going to shift 1, 2, 3, left and down 1, 2. So 0, 0 ends up where? Good. -3, -2. Good. Okay. So again, we started here, reflected it, didn't do anything. Stretched it, didn't do anything. Compressed it, didn't do anything. And then finally, it started doing something when we shifted it. Right? Okay. Let's do 1, 1 to start with. 1, 1, first thing we reflect it. So where does it end up? -1, 1. We're over, 1 negative when we're down here, right? We're reflecting it down, right? So first it goes to here. I want to erase these arrows in a second, so you don't need to draw the arrows. Just say where we're going, okay? Reflect it, then what happens? Stretches it by a factor of 4. So instead of at -1, it's going to go to this point has a y coordinate of -1. What's it going to end up being? -4. Yeah, it's just going to go down to here, right? I'm going to erase these arrows. So like I said, don't draw the arrows. I'm just trying to show you where they jump to. Unless you want to draw the arrows for your own personal edification or whatever. All right, what happens next now? Yeah, compressing, right? This is now the point 1, -4. What are we going to do now? We're going to multiply the x by 1/3. So it ends up here, right? Goes to here. So now we're at 1/3 -4. Now what happens? Shift left 3. So 1, 2, 3. It ends up here. And then finally it goes, which way? Down 2. So 1, 2. So this point ends up at where? So we started at 1, 1, and it ends up at then 1, 2, 3, 4, 5, 6. -6. So like I said, I'm going to erase all of these. I was just writing it along so we could figure out trace it where it went to. Okay. So again, we flipped, multiplied, compressed, and then shifted and shifted. Let's do the next one. Where does this one end up here? We're at 8, 2 to start with, right? Right? We're at 8, 2. First thing we do is what? Reflect it. So it's down here. 8, 2 then becomes 8, -2, and I'm not on the right spot down here. Becomes 8 -2, right? What happened next? Stretch vertically by a factor of 4. So what do you end up doing with that -2? What does it become? -8, because you're multiplying it by 4, right? 1, 2, 3, 4, 5, 6, 7, 8. Then what did you do? Compress by a third, right? Which way? Yeah, the x-axis, right? So it means when we compress by a third, it means we take all the x's and divide them by 3. So instead of here being at 8, we'll be at 8/3, which is 2 2/3. And then what do? Shift it left by 3. 1, 2, 3. Which makes it at -1/3, 8. -8. And then finally, which way does it go down? Goes down 2. So what's your y coordinate going to be there? -10. So your point that's at 8, 2 ends up at -1/3, -10. So your graph now is looking like this on this side, right? So what's going to happen on the other side? Basically, it's going to look the same. It's just going to go the other way, right? We have the symmetry of the graph. I didn't draw that very well at all. Like so. The graph is symmetric, so it'll look like the same idea on the other side. What questions do you have? Like I said, one of the reasons why I wanted to focus on tracking those points is because, like I said, in WebAssign, it's going to ask you to do that. Being able to follow along with the transformations and figure out where the points end up. There's a couple of problems like that on WebAssign. What questions do you have? Well, let's go the other way. In the problems we've done so far, it's given us a function and asks us to identify the transformations. In this particular problem, it gives you the transformations and then says write the function. So the first one says start with square root of x, stretch horizontally by a factor of 3, reflect it across the x-axis, move it up 2. Let's do the last 2 first, and then we'll worry about the horizontal piece, okay? If I start with square root of x, and I'm purposely leaving spaces in there so I can write things. If I start with square root of x, and it tells us to name the function g of x, I have the g of x there. In order to reflect it about the x-axis, what do you need to do to the function? What gives you reflections? Negatives, right? Is this one asking you to reflect it horizontally or vertically? Vertically. So does it need to go on the inside or the out? Out, right? So I need to put a negative on the outside, right? That handles the reflect. That's why I'm trying to do the last 2 first. We'll handle the horizontal one here, the stretch horizontal here in a second. Okay? Does that make sense? Okay so far? It says move it 2 units up. What do I need to do to move the whole graph up? Good. Plus 2 on the outside, right? That's going to take care of our vertical shift up. Now let's handle our horizontal stretch. Remember, in the last problem that we just did, we had a 3 multiplied by the x, and we said we compressed it by a third, right? We did the opposite. This one now says stretch it horizontally by 3, right? In order to stretch it, what do you think we need to put on the x? A 1/3. Good. That's exactly right. Remember again, it does the exact opposite of what you think it should, right? In order to stretch it horizontally by 3, that means we need to multiply all the x's by 3. But the transformations on the inside do exactly the opposite of what you think they should, right? So instead of multiplying by 3, we'll multiply by 1/3. Okay? Just like in the previous example, there was a 3 in there, and we said it compressed it by a factor of 1/3. We multiplied all of the x's by 1/3 or divided them by 3, right? We're doing the exact opposite idea here. So this would be your final function then. It does the 3 things. This is your stretch by a factor of 3. This is your reflected horizontally, reflected vertically. Sorry, about the x-axis. I read the horizontally on the problem as I was talking. And then the +2 is the shifted up. Okay. Let's do the next one. We start with x to the 4th. We want to compress vertically by a factor of 1/2. What needs to happen in order to compress it vertically by a factor of 1/2? So if it's going to be vertically, does it go inside or outside the function? Outside, because it's affecting the y's, right? Okay. So what do I need to put on the outside in order to compress it vertically by 1/2? What do the negatives do again? Negatives always, they do reflections, right? They either flip this way or this way, right? So in order to get it to be compressed vertically by a factor of 1/2, that means multiply all the y's by 1/2. So what do we need to do? Yeah, just put 1/2 out in front. Good. If I'm going to compress vertically by a factor of 1/2, there needs to be a 1/2 out in front. Let's do the last one. Let's do the move it down 3 units. If I want to move it down 3 units, what do we need to do? Subtract 3 where? On the outside. Good. Yep, to move it down 3 units, I need to subtract 3 on the outside. That handled all the vertical ones, right? We compressed it and we've moved it down. Yeah? That part okay? Let's do the horizontal shift before we worry about the reflection. Move it right 2 units. Yeah, put a -2 inside the parentheses like that, right? I need an x -2. We agree with that? Okay. Finally, notice I handled the reflection on the inside last, only because I made sure I mentioned the next piece. Reflection across the y-axis affects what? X's or y's? The horizontal transformation or a vertical transformation? Horizontal, right? Flipping it this way, right? Right? If it affects the horizontal, if it affects the x's, it needs to go on the inside, right? To do a reflection, we put a negative, but remember again, I told you when we handle these things, I want to factor out the coefficients, so we'll put a negative like that to make the reflection. Just like I talked about when the first thing we did was factor out the coefficient, right? Now, this one we started with x to the 4th. What happens when you take a 4th power of a negative? What does it become? A positive. So really, I don't even need this thing in here. The reflection doesn't do anything. according to what the transformations it gave us, we put the negative in there. It turns out we don't really need it for this particular problem. Generally speaking, we do, but for this particular problem, we don't. So again, look at reading from left to right. We did a vertical compression. We did a horizontal reflection, horizontal shift, vertical shift, right? Just reading like we did when we graphed them, reading it from left to right. And that should match what they gave us for the descriptions. What questions do you have on that one? All right. One last thing they talk about in this section that apparently I don't have examples on here, that's okay, is the idea of a function being even or odd. So let me write this. Down here. I meant to have examples on here, and I apparently don't have them. That's okay. Good news is you got some blank sheets in the back if you want to keep it on the same thing. All right, so to start this discussion, let's remind ourselves of some base graphs that we've already talked about. What does y equals x squared look like? Yeah, it goes this way, right? Is that nice U shape this way? What would happen to that parabola, that U-shaped graph, if you reflected it across the y-axis? It would look exactly, if we do it across the y-axis this way, it would look exactly the same, right? It would land on top of itself, right? Okay. What if I do y equals x cubed? What does it look like? It's a nice kind of S-shape idea, right? That way. If I take y equals x cubed and I turn it upside down, what do you notice? So I literally just take it and turn it upside down. Take your paper and rotate it 180 degrees. What happens? Looks exactly the same, right? Okay. If I do x to the fourth, what does an x to the fourth graph look like? Kind of look like x squared, right? A little steeper on the ends, a little flatter in the middle, but exactly the same. So again, I ask you, if I flip it across the y-axis, what happens? Nothing. It looks the same. If I do y equals x to the fifth, what does it look like? Similar to the x cubed. If I turn it upside down, it looks exactly the same. What do you notice about the powers that we're talking about? X squared, x to the fourth, the powers are even. X cubed, x to the fifth, the powers are odd. So even and odd functions are talking something about graphical symmetry. Okay? So we say a function y equals f of x is even if the graph is symmetric with respect to the y-axis symmetric with respect to the y-axis just means exactly what I said a minute ago. If you take the graph and flip it across the y-axis, it doesn't change the graph. That's what symmetric with respect to the y-axis means. Okay? We say a function y equals f of x is odd if the graph is symmetric with respect to the origin. Symmetric with respect to the origin means that if I turn the graph 180 degrees, turn it upside down, it looks exactly the same. That's what graphically what symmetric with respect to the origin means. Certainly, you can think of graphs that are not symmetric with respect to the x or the symmetric with respect to the y-axis or symmetric with respect to the origin, and then we just say those are neither even nor odd. Okay. So it can be even, odd, or neither. All right, so those are the possibilities. We don't want to have to make a graph every single time in order to determine whether something is even or odd. Okay? We want to have an algebraic idea. Well, notice if I start with a point x, y, and I want to reflect it across the y-axis, remember that's multiplying all your x coordinates by -1, right? That's what reflecting across the y-axis does. It just takes all your x's and multiplies them by a negative. That's how it flip-flops them. If I do that, does the y value change? If I multiply the x coordinate by a negative, does the y value change? No. Okay? So this gives us our algebraic way to determine if a function is even or not. Y equals f of x is even if, when we replace x with negative x, we get the exact same output. So if I take out x, substitute in minus x, and simplify, we get the exact same thing we started with. Knowing what we know about transformations, this says that a horizontal reflection did nothing. Algebraically, that's what this says. A horizontal reflection did nothing. For odd, notice if I start with x, y here, if I rotate it upside down, that point ends up over here at negative x, negative y, right? It makes the x negative and it makes the y negative. So if I put in negative x, I should get out the negative of y, right? So y equals f of x is odd if when you put negative x in for x, you get the exact opposite out for f of x. Literally everything's been multiplied by -1. So let's do an example or two here, emphasizing what we're talking about. Let's say we have the function f of x equals 4x squared plus 8. The problems will ask you, is the function even, odd, or neither? That's what it'll ask you, okay? Doesn't matter if it asks you if it's even or odd or neither. Your first step is to take out the x and replace it with negative x. And then simplify. If I simplify this, when you square a negative, what happens to the negative? Yeah, it disappears. It makes it positive, right? Is what I have here exactly what we started off with? Literally the same function. Is it the same function? Yeah. So this is even. Good. Let's start with a little bit more complicated function. Let's say our function is x over x to the 4th plus 3x squared. Again, if you're asked whether it's even, odd, or neither, your first step is always replace the x's with minus x every single time, okay? So I do f of negative x equals negative x over negative x plus 4 plus 3 times negative x squared. What does your denominator simplify to? What it started as, right? We're doing even powers of negatives. The even powers just kill that off. Notice I have negative x on top. I can take that negative sign and pull it out all the way out in front. Do we have exactly the same thing we started with? No. Do we have exactly the opposite of what we started with? Yes. So what will we say this function is? Odd. Good. Let's do one more. Let's say we have the function f of x equals 3x cubed minus 7x plus 2. Again, first step is to replace the x's with negative x. So we compute f of negative x. So I have 3 times the quantity negative x cubed minus 7 times the negative x plus 2. And then we simplify. What happens when you cube a negative? It stays negative. So I can redo that as negative 3x cubed minus a minus here makes a positive 7x plus 2. Is this exactly the same thing you started with? No. Is it exactly the negative of what you started with? No, not quite, right? We've negated the first term. We negated the second term, but notice that your constant term stayed the same, right? So in this case, f is neither even nor odd. And again, the names even and odd come from the fact that we're looking at even powers of x's or odd powers of x's, generally speaking. We also use these names for other types of functions as well. But notice that in this last example, I mixed my powers up in my polynomial, didn't I? I've got odd power here, but that has an even power of x, doesn't it? That's like an x to the 0, right? So I mixed it up. When you mix and match in a polynomial, it will be neither. This, I'm doing one polynomial divided by another, so there's a different rule for that type of function. But for polynomials, for a polynomial, remember polynomial means all your x's have positive integer factors. Or exponents, I mean. You're not dividing by x's or putting them in square roots or any of those kinds of things. For your polynomials, in order for it to be even, all the powers of x have to be even. In order for it to be odd, all the powers have to be odd for polynomials. So remember that we have an exam on Monday. Your exam is over 2.1 through 2.5. I gave you a review sheet last time in class. If you need another one, I think I've got some extras here, but they're also posted on Moodle. The one I handed out in class says review in class. It has solutions. There's also a second review sheet on Moodle as well that you can also go through and work on problems for that. Okay?
I will be using that practice exam during today's SI session. So if you want to come review for the exam at noon to 1, then feel free to pop in.
And your math center will be open from 6 to 8 on Sunday as well. So you can always email me too. All right. Have a good weekend.
Yeah.
Don't rip it. Okay, there you go.
Thank you.
You're welcome.
Have a good day.
You too.